Okay, welcome back to another installment of AI BDS1. So we're gonna continue from where we were last time. Just sort my Zoom elements here a little bit. All right. So last time we started talking about data understanding. And what we did was we said, okay, first, what is data, right? So this was kind of the first idea. What is data? What kind of types of data are there? And so basically, what was really important was that we also, in every aspect, kind of had an idea on how we could make these vast data rows. Usually we have large amounts of data, but by large amounts of data, I usually mean a large amount of either rows or columns or both, right? So this is when people talk about large amounts of data, they just mean a lot of columns, a lot of rows, right? So how does a data table look, and so on and so on. So, and then we thought, okay, it would be nice if we could actually like summarize the data to get an idea on how the data looks like. And then we discovered we discovered univariate analysis, which we did most of the time. We said, okay, there are numbers, we call them statistics. They summarize the whole data set, or summarize one variable of the data set. That's why it's called univariate, because it summarizes one variable. And if I do this for every variable, then can summarize somehow the distribution of these variables in the data set. So, and then we also said there are some visual aids, and we started with the histogram. And then I told you, okay, the histogram is a univariate graphic that helps us to understand what is called the distribution. And now again, why is this important for predictive modeling? Because we need to have the distribution to know, okay, what kind of values are interesting to us and what kind of values are not interesting to us. Now, the problem is we do not yet know what kind of values are of interest for us, because we need to somehow see how these values of that variable here, because this is one variable, influences our target variable, right? Because this is the thing we want to look at. So, and then after we found out, it could be that for some rare values, the target variable behaves very differently. And then we have the problem that we do not have enough data to teach the model this. So going back, using my analogy of the parking lot, because everything here is about the actual parking lot, right? So remember the whole analogy with the little child and the parking lot. So we teach the little child what's a sports car, and we go through a parking lot saying that's a sports car, this is a sports car, this is not a sports car, right? So, and now imagine that in the parking lot we have some sports cars that are definitely sports cars, but they have some features that are rarely seen, right? And one of these features could be this feature. So this feature, some expression of the feature. For example, um, it has like a sticker of a racing team on the side, right? You could imagine not every car has a racing team sticker, but saying it has a racing team could be a highly indicative feature for that being a sports car, right? We could imagine that, right? So imagine now that we only have a few of these cars, right? And then we could not really see the meaning of this feature. And then we could identify it by looking at the distribution and seeing, okay, it's rare. And then we could use bivariate analysis, which we will talk about in a second, to actually see how these values correlate with the actual variable, right? With the actual target variable. Sports car, yes, no, in the example of the parking lot, and so on. So it's always good to use like some kind of graphics to look at the variable distribution to see how, and this is probably maybe the most important sense, how much um how much power, and we can, when I say power, I mean how much information lie within the different areas. And this will help us. The next thing is called a histogram. You know probably what a histogram is, will help us to get an idea of that. So, and So the histogram, what it does is it takes data and it puts it into bins, right? So we can imagine a bin and I have to define the bin. So you can see I have an example here, age of person, age of 10 persons. Again, it's the age example. And so I can define how I want to like split this up into bins, right? So the bins you can see here, I have two bins. First, I have a bin size of 20 years. That means I have like this bin and that bin. So I have from 15 to 35, which is the first bin, 20 years. And then the second bin is from 35 to 55, 20 years again. So I can see not much information, but if this is what I desire, I can see there is a large amount of data here and less amount of data here. Now, again, what does this mean for predictive modeling? Now I know that here I have less data. That means when I teach, right, when I teach the model, it will mainly look at this part of the data. Again, if I supply the child with this kind of data distribution, it will mainly look at this part because this part right here is just underrepresented, right? And so this could be a problem. This simply could be a problem. Now, if there was some kind of, again, we need to check if there is some kind of relation. Otherwise, it isn't a problem at all. And what I can also do, like here I have bin size of 5 here, so we see it more fine granularly. We see here there is some data, and it looks completely different. This is because I choose like a different idea of how to split it up, right? However, this helps me to know that, for example, here we also have like another data situation. We don't have as much data as here, and the model learns how it learns. Like you take the child, and the child will see what it sees. And if it doesn't see enough, you cannot learn enough. Again, imagine you prepare for a math exam, right? So this is the same analogy. And you calculate a lot of tasks all the time, right? And you calculate tasks of type 1, you calculate tasks of type 2, and maybe of type 3. And then you have like one or two tasks of type 4, but you don't have as many, right? And what you suspect is, because you are now the model that gets taught, you suspect is that this is not as important, that this is not as important, right? Because there are the only two tasks, and maybe I will not learn this at all, right? So because the other types, I will mainly use the other types of learning, and I will do this, right? So even worse, let's say you have two types of tasks, like here in the left-hand side, where I choose bin size 20. Let's say you have this situation. Like you would say, okay, I will prepare like a lot for this, and maybe I will calculate one or two tasks of this, right? And then you don't know in the future, which we predict, what the situation will be. It could just be that your training data is bad. You do not know. It could be that the real distribution of tasks looks completely different. You just didn't get an actual good representation of the real data, right? So, and this will be a problem for you because then you will get a bad grade because you just calculated two tasks here and it will like maybe a lot of these question types will come up. And this is why when we talk about machine learning, right? So again, the goal is not to reintroduce you to histograms. You know what histograms are, I suspect you know. It's about using this to get an idea of probable pitfalls that we will see later on, that can happen later on when we say, okay, oh, this looks like we need to like pay attention here, right? So, and we now know that the data situation, it's not as bad as some other situations, but if we look at this, maybe, and we're interested in particular here, that this, and we find out in bivariate analysis that this kind of, we have a lot of indication here, then this will be problematic because the model will then mainly focus on these values, right? Obviously, because we have simply more data here. So more cases to support. It's just what it is, right? So what the machine learning model cannot do, what you can do as a student, you can say, oh, I don't have enough of this task type. I better get 10 more tasks somewhere. I better ask the professor, or I better ask the other semesters if they have something, right? So you are able to to work through that and say, hey, I probably need more tasks. The machine learning model can only take what it gets, what you provide to the model. Okay. This is why you have to make sure that you provide correct to the model, a correct amount of data, correct data distribution of features and of target variable, right? So this here is true of features and target variable, right? So if the target variable, this gets even worse. So don't get me started on imbalancing the target variable, but we will talk about this separately because it's a highly problematic topic. Okay, and this is again another thing where we can use this. So in univariate analysis, when we have a histogram, we can see this right here. So this is called skewness. So this is what we oftentimes see, right? This is what we oftentimes see. And this is basically what I just told you is that we have, if it looks something like this, right? So if we look at the left or at the right hand side, like this is the only difference is skewed right and skewed left distribution. So it doesn't really matter. Like you look at it and you see, okay, some part we have a lot of data, like here we have a lot of the data, and here we do not have a lot of data. However, we have, however, it's there, right? It's not like it's not there. And now I feel like we've touched on this a little bit, and having the knowledge of what I just said, that this data will be considered, but of course not as much as this part of the data. But we don't know how important this is, right? We assume automatically that the training data that we have represents this, but we have less cases here. And this means that the model will not probably will have a poorer prediction quality for these cases than for these cases. Obviously, because we just trained for a very small amount of these cases, right? If you want like to have an analogy, use the math test analogy or use the parking lot analogy where you say, okay, if the child only saw two cars looking like this out of 10,000, the child will not know well what to do with the combination of variables. Also, this is univariate, right? But then again, it's about the combination of variables. So what happens if this variable, as I said, this is univariate, what happens if some of these rare values combine with other values from other variables? Because this is what makes the model, like a combination of all these variables leads to sports car, yes or no, leads to you passing the math test or not, right? So it's not about like the single variable has an influence and then you pass this. No. It's a combination. Like it's always a combination. This is why we put a lot of variables in there, right? So, so in univariate, we can see that this variable, this one variable, doesn't have quite a large amount here. And so whatever we do with this amount could be problematic for the model later on. Why? Because we don't have as much data as we might hoped, right? So, and in this case, this is called skewed. So when I have something like this, right, the thing I'm gonna do is like I might need to put weight on the long tail. So I might also need to balance the X variables, right, the features, and say, okay, I'm gonna cut some of this data because it could be that this is very important. So I might have to filter out some of the data here that has some of the cases that are like the usual cases, right? So to minimize the errors. Okay. However, this will give you an idea on just the data situation. You will see, okay, there is a problematic. Like the best thing, of course, would be like you have some symmetric distribution, but usually you will encounter something like this. And this could also be, it could also be that it just is what it is, and these cases are not important at all, right? So that's just the natural flow that you have, that it's okay for your prediction model if you have these cases, and this is what happens most of the time, and this could be okay, right? But again, we started with business understanding, right? And business understanding have some restrictions on the prediction quality. Like again, let's say you have a manufacturing process and this is like the temperature curve. So imagine that, of course, usually I have normal temperatures, right? But when the temperature gets bad, this is usually where the manufacturing pieces break, where they start to get errors, right? So this is the important area for us, right? And in the combination with other variables. So maybe this doesn't necessarily mean a high temperature does mean nothing, but if the vibration also rises, then this combination could mean that there is a tendency of this thing to break. However, we have only a small amount of data and probably even less with high vibration. So these combinations are totally they are rare, so that the model doesn't really focus on them, right? So it has a lot of, and also a lot of times it will just predict it's okay, it's okay, it's okay, it's okay, and then it doesn't know in the few cases where it's not okay. It's problematic. So it's not per se that models cannot like learn this. I mean, if you see, okay, this and that will always lead to a problem, and you see it 3 times, then this is what your model will learn, right? But if it's more complex than that, if there are more variables involved, more combinations of variables, more nonlinear combinations, that it will get harder. Like if it's very easy, you can also put this data situation in any model and there will not be any problem, right? So I'm not talking about the easy combinations. I'm talking about things where why we actually need machine learning for, because we want the machine learning to do the combinations and everything for us, specifically later on in deep learning. Okay. So now you know why this could be a problem, but only could. It doesn't have to be a problem. So I want you to know that your critical thinking is needed here to see, okay, um, I know potentially I have less data here, but it could be a problem or maybe not. Okay, now imbalanced data and outliers. So I want to address this because this is also something a lot of students always write, and they love the word outliers, like, oh, outliers, 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 and imbalanced data. So what we've talked about here is univariate generally. So this is true for this we can display, of course, for the target variable as well as the any of the feature variables, right? Now, the first thing I want to talk about, having that in mind, is the thing below, which is not outliers, but is imbalanced target variable because it fits to this. So an imbalanced target variable. So for example, let's say we have a classification. That means we have a target variable. A classification means a target variable is not numerically has no numerical scale, but has like somewhat of a class structure. So that means it's either ordinal or probably even nominal. So we have, for example, this thing right here where we have credit card fraud, yes or no, or fraud and legal. So legal credit card transactions and fraud. And as I said, usually we have a lot more people are not fraudulent, right? So I hope none of you had committed credit card fraud. So only a few people. So again, I have less data from them. Like this is exactly the situation. But now it gets worse because now it is the target variable. It's the target variable itself that is imbalanced, right? That is skewed. So we can see here the same phenomenon, but it's just two, but it's the same phenomenon as here, just in a binary way. So this is skewed, and we call this for when we talk about the target variable imbalanced, and we can see this like, yeah, if we just have like some kind of charts here. Okay, we will talk about this a lot in data preparation, so I don't want to spoil it. I just want to show you how we can easily look at this. So you should always look at the distribution of your target variable, right? And no matter if it's a regression problem. So in a regression problem, it will look like something like this, right? And in a classification problem, it will more likely look something like this, where you have less bins, obviously, right? So here also you see this is not a histogram, right? This is a bar chart, right? We just have 2 bars and we just count legal and fraud. So we basically just count the 2 options, right? So this is just a count. This is a bar chart, right? So basically, so we don't have to put bins again. In a histogram, we need to put bins, but here we cannot separate because it's not a numerical variable. So technically we can also call this a histogram, but it's just a binary histogram with 2 bins, which is legal and fraud, and then we count it. So the y-axis is the same, like here, it's the count, it's the frequency, but the x-axis is just the class of the of the 2 variables, right? Of the variable class, either it's legal or it's fraud. Okay, so outliers, as I talked to you, so we have the box plot, the well-known box plot that I introduced to you, so we can see outliers right here. And outliers, we will talk about separately also in the data preparation, just so you know, we can see them because they are outside of the usual distribution. So we also can talk about mass, right? So where's the mass located? So here we have the mass of data is located here. And we see it gets smaller. Now, if we have nothing, nothing, nothing here, and here is then one kind of thing that would also be like an outlier. But we also see outliers in this kind of box plot, right? Where we say, okay, it's outside of the range of the normal, right? And this is what an outlier is, outside of the range of the normal. And this is somewhat philosophical. We discussed it a little bit last time where I said, okay, what I personally do is like I talk about anomalies, so that are things that can happen, right? That are normal, that are happen, that are interested to us, and then there are kind of outliers that could also be just generated by mistake. This is the easiest part when they are just generated by mistake, when they are not actually part of the data generating mechanism, right? Talk about data generating mechanism at the end of the lecture. However, outliers will be a problem for us, but we will talk about this in data preparation. Okay. Now, an important thing, because we discussed it and also the chat like chipped in here. For example, Tristan said we can't calculate with IDs and so on. And we can see this here, right? So this is like, again, an idea on the scale level and what we can do with them. So this table is probably important for you. You can see, okay, to check, okay, nominal, we can only have the mode, so we can only count, like you can see it right here. So this is basically just a count, right? So if I would like, what's the mode? What's the mode of the target variable here? What's the mode here? Can put it in the chat. What's the mode of this variable? Right? So the mode is the value that appears most often with the highest frequency. What's the mode of this variable? So while you think about the mode of the variable, let's go on. In Ordinal, we can also have the mode, like the most frequent value. We can say this is or it isn't. Like we can say it is. The mode could be very good, for example. And we can also calculate the median. Like we can order them and then have like the value that is in the middle. We can order very good, very good, very good, very good, very good, and then somewhere in the middle, and we have the mode. We cannot calculate the mean. Like this is not possible, cannot calculate the variance because we need intervals for both of them. We need to calculate differences, and we cannot calculate the difference between very good and good. We know that very good is better than good, but we don't know by how much, and this is the difference. And so, of course, with interval and ratio scale, we can calculate all of these things. So let's check the answers. Legal, legal, exactly. So here, of course, the mode is legal. We see that the frequency of legal is higher. So just a quick question to check if you're still awake. Okay, so, and these tools will help us also, as I said, this is why I put this slide here to define data problems that we later need to fix in data preparation. And this is our link later on. But now, as you said, I discussed a lot about how this univariate analysis, how it functions and how it could influence our prediction. But in order to see, and I also oftentimes told, well, we have to see how important this variable is that we univariately looked at for our target variable, because this is the one we predict. And there we can do bivariate analysis. So we can do this for nominal correlation. So this is usually the tool is correlation to see how they work together. I don't want to go here into detail. This is not really extremely important, to be honest, right? And you learned it in statistics. I just want to give you, this is like a short refresher. I don't want to strain it too much. Like if we have two nominal variables, like this could be employed, could be, for example, the target variable, and gender could be the input variable. And then we could have like such a table and calculate contingency coefficient from a contingency table. And then we see, okay, large correlation will result in a large coefficient and so on, right? So it's based on a chi-square thing. The idea is that they are independent from each other, and then you have like you basically in your mind draw a table. How would it look like if they are independent from each other? Then you look at the actual table and you calculate just how different it is. That's the idea. And for ordinal and interval correlation, we have with ordinal data, we use rank correlation. The formula is the same, but in ordinal data, you use the ranks, right? And in interval or ratio data, you just use the actual numbers, right? So you can see it here. So if you need an example, just look at this. I won't let you calculate correlations in the Excel. It's just as simple as that. You can do that in a statistics exam. Like the aim here is not to let you do easy statistic tasks, but it's rather the idea of you figuring out why this is important and why we do this. And the importance of correlation is, does a variable has to do something with a target variable? Is there an influence, right? And then this is more important than this might matter, right? Or this might matter here, right? When we have an imbalanced target variable, and then we have also like imbalanced feature variables, and that combination could be problematic. So we need to do something in the data, right? We have data problems that we need to solve for data preparation. So this is an important diagnostic tool, right? But if the variables, we need to check if the variables are actually important. So, so this is like the process. Okay, check, okay, look at the variables and check if they are actually important. So if there's no problem, then it doesn't matter. If there's a problem and they are important, this is the combination that matters. Okay, so it's basically it. So just know, okay, it lies between -1 and 1. We know that. So you've learned this in statistics, right? So we can see this. A thing I want to tell you, however, very important about correlation is, you can see this right here. This is why I put this little image here. Correlation is always linear. The correlation coefficient assumes a linear correlation. Like if you have like quadratic correlation or other forms of correlation, then this will not be very good. So what, for example, let me show you an example. So here, like I have two variables, x1 and x2. And I want to have the correlation between them. And it looks something like this. And I calculate now the correlation coefficient, like this one right here, like the linear, and it would look like this basically, maybe something like this. Maybe even a little bit higher up, but it would look something like this, right? And it would not be that great, right? Now, when actually the true idea here is that it is actually something like this, maybe more a quadratic correlation. This would be a high quadratic correlation, but this correlation coefficient does not account for that. Very important. And machine learning is actually, the job of machine learning is actually to go beyond like these linear combinations, go like to nonlinear things. And we will learn this. While we go along. We will learn this in modeling. And this is why we can do this. But actually, to be honest, what we will usually do is like, this is something we do in statistics more than we do in machine learning. Because in machine learning, we will go through the process of on providing a very good data set for our prediction model, right? And then just more or less iterate the process, the CRISP-DM process from data understanding, data preparation, modeling, evaluation. And we look at the evaluation and see, okay, we need to like either get more data, we go back, right? We need to prepare the data better, go back to data preparation. We need to use other models, go back to modeling, right? So where we go back, we have to decide, but it's more like we iterate through this to get a better model somehow, right? We prepare the data better, we take better models, we configure better models, and so on. We try to do our best, but usually we don't do this statistical thing because of the fact that a lot of these things that we can detect are just of linear nature, and we want to detect all kinds of variables that go together also in a nonlinear way, right? So, and always imagine that what I put in here is just a typical statistic thing where I said, okay, we have x1 and x2. So we have two variables. This is bivariate because it says bivariate. Now, what I told you though is there could be like an interaction effect, and this interaction effect could have an effect with another variable. So it could very well be that we have x1 times x2 squared, for example. So this could just be the thing we're looking for. So, and this then could correlate, for example, with, oh, let's remove this. Sorry, this was the wrong axis. Just move this because I would actually. So let's say this is y, this is our y variable, and here we have x1 times x2 squared, for example. So this could be a term that this could be a cool feature that we use itself. So x1 with x2 squared. So this combination could be the information I'm needing, and this could be like a quadratic thing, and this will never be caught by using bivariate analysis. So this is why with bivariate analysis, we only get like from all the things we can do. If these are all the things we can do, bivariate analysis is maybe only a small thing. So basically what we usually decide to do, and not always, sometimes we do it because it's apparent and we have data like the Titanic data set that I introduced for the people that were actually here in the beginning. We say, okay, we do this, but we don't want to exaggerate that. It's like if you have, imagine you have like 10,000 columns with sensor data filled with sensor data, you don't want to do this bivariate analysis. It's just, what does it do? You just build a model and see if the data can predict the model, right? So this is why we do it instead, because usually instead we are really interested in the correlation of two variables, because we're not interested in what the influence of X on Y is. But in machine learning, we're interested to predict Y as good as possible. In statistics, we do not really care if Y is good predicted. We just want to say, oh, this variable has an influence. Like, yeah, but 1,000 other variables might have two, right? So our question is a different question. So this is why we need a good prediction. So we throw every data in we have, like something like this, and and want to build a model that can detect these things. This is our ultimate goal. And therefore, we have to provide data we have to provide data because this is the data we put in, right? So we have to provide a good parking lot. Like our job in machine learning is to provide a good parking lot, right? And not to overanalyze the parking. We will need to analyze the parking lot to ensure it is good, but this includes things like this, things like that here, right? Things like this, looking at the variables, things like looking at outliers, things like this. This is ensuring that we have a lot of representative data in the parking lot to teach a good model. This is our main goal, right? Okay. So other visualizations, if you like, there are a lot of other visualizations here. Analytical dashboard, arc diagram, scatter matrix. Scatter matrix, you have oftentimes parallel coordinates like Cliff plot, Andrews plot, and so on. Like there are a lot of things to actually see what multivariate data looks like, right? But generally, we will resort to these basic things like univariate box plot and like these pie charts, bar charts, or histograms, right? Okay, so now I want to use an example that I already introduced in the last lecture to bridge the gap to data preparation, which will be our next topic. So, and I've uploaded this also in e-learning. I've prepared this for you as I promised you I would not only smother it on the slide, but also if it's important, if you can use it to prepare it for you, right? So this was like something I promised, and yeah, I try to keep my promises. And so you can download this. Let me just see if I can get here, but I want it in red. Yes. Okay. Let's see. Does it work? Okay. It works. Okay. So let me zoom in a little bit so you can actually see it. So we will go over. So this is just an example, right? So this is an example of data. And this is also, again, some practical advice to round up the lecture and to give to give an arc towards data preparation, right? Because in data preparation, we actually deal with a lot of variables. We deal with transforming variables. And sometimes I'm asked like, okay, but data understanding is only we do analysis. Yeah, but it's also like we also need to transform the data beforehand. So if you want, there is also a short interaction between data understanding and data preparation. So usually this is how it goes, right? So we have business understanding and then actually use this smart business understanding. And then there's actually, we see, okay, we look at the data and we see, okay, it doesn't really fulfill the format that we are looking for because we have a goal here, right? The business understanding defines a goal for us, right? And for this goal, the data needs to look a certain way. If you want to predict something, this variable needs to be in the data set and all the information needs to be in one row. This is very important. And I will show you what I mean by this example. So data understanding and data preparation usually have this, in the beginning, this frequent iterative thing where we look at the data, then we need to transform the data a little bit, the table of the data, and so on. So let me introduce you the example. This is actually an example I already introduced in the last lecture, right? So this is the sensor data example, exactly the same actually. So scenario is the following. Again, manufacturing scenario. I love to use it because it has a lot of data naturally. So imagine we have a machine, call it M1, like in the operations research class that you are, you love to call machines M1 to M2, right? So let's call it M1 with sensor readings at a time, right? We have S1 is the temperature in degrees Celsius, S2 is the vibration strength from 1 to 10. So we have these two sensor readings, right? And then we have a log file from which we can extract when an error occurs, time and type of error. So what I mean is, from the beginning, we have two types of data, right? So this is just like the raw data situation, and this is optional, right? This is optional for you because this is a little bit of IT, optional. So the DB structure, the database structure here would be here. We have the actual sensor data, right? We have the sensor data. So the sensor data is structured. Obviously, it's just time and sensor, time and sensor. And then we have another kind of database where we have documents, right? So semi-structured documents called log files, right? So, and then in the log file, there at some point we have a time. So I'm going to zoom in a little bit. So we have time. So for example, 12:15, and then there is failure, right? And the log file will not like document 12:10, everything's good. 12:15, failure. 12:20, everything's good. We'll just put the time here and when something happens. This is an event log, right? So maybe even call it event log. So an event log will just log when something happens, that it's worth put out. So, and then the first task is to have the sensor readings, which are a table, right? To match them somehow, right? To put them together and to put them in one data table that we can later use to model it, right? So this is data understanding. We look at the data, we look how it's located, and data preparation, we look how it's prepared. And this is what we want to do. So, what we have here is, since this was optional, so we have raw but already joined data. So we already have a raw, but we have joined data, right? So that means we have joined them, obviously, by the thing we know, by the timestamp, because here we have a timestamp and here we have a timestamp, right? So somehow there's 12:15 also here, and then we can join them. The problem now is that so this says error, failure, error, and then maybe it gives an error type. So in my example, I have 10 error types, right? So time and type of error. So I have 10 error types. So 12:15 failure, and it puts out error 1 at 12:15. Okay. So here the table looks as following. So I have a sensor reading every 15 seconds, which is realistic, which is a realistic distribution, which is a realistic resolution of sensor readings. So For the sake of easiness, I have like only two sensors. In the example, in the last lecture, we had a lot more, right? So usually here we have a lot more sensors, right? But just imagine way more colors, but it doesn't change the story here. Okay, so we have a time, we have a sensor reading, like remember, sensor 1 is temperature, degrees Celsius, sensor 2 is vibration strength on a 1 to 10, right? So, and then we have, at some point, we have an error here, error type, right? So we have an error type, and the error type is relatively simple, can be E1 to E10, right? So the problem is that I have these sensor readings every 15 seconds. But now at some point here, so obviously there are some lines missing. So at some point there is an error. And for this error, of course, I don't have a sensor reading because at the exact time there might not be a sensor reading. Okay, so I cannot assume this, right? So, so how do we do it now? Because what do we need if we want to predict this error? We want to predict this error. And this is very important advice. How do we do it, right? Because, and this is probably the most important thing, why we do this iteration between data understanding and data preparation is not only that we give good data, but we give actually data that works, right? So a data format, a data table where we can actually learn. And a data format where we can actually learn from always looks like this. We have a y variable here, right? And here we have some x variables. So this is some features, right? So this is always the format we need. So we need what? And then each row needs to be one training example. This is very important. Training example. Training example. So each of these rows needs one training example. Remember how machine learning works. I take the child, I put over the parking lot, and each training example, this is one car. So in the park, using the parking lot analogy, this is one car. I show the child, right? And I should say to the child, this is a sports car. Look at the car. So look at the features of the car. Hello, child, look at the features of the car. This is a sports car. Now I go to the next car. Hey, this is not a sports car. Look at the features of the car. This format is the format I need. And so I cannot use this format. Why? Because at this line, there is no y variable. In this line, there is no y variable. In this line, there's a y variable, but there are no x variables. I cannot use it. And this is why you always have to think of a way of transforming the data into this format. This is very important. This is exactly what you need to do. And you have to figure out how you can do it. There are a million ways to do it. You lose a lot of information. I have only one way. I have one particular way here of doing it, but you can do it other. We will discuss this, right? So one thing we can do is we need to put the levels together, right? Obviously, the most important thing for us is the y variable. So we need a y variable in each line. There is nothing more that we can do. So what we need to do is we need to generate, basically, we need to have an idea on how we can build such a thing. And the idea is that we use the y variable as a central idea. So we know we look whenever an error occurs, right? We have this, and then we have a time window from that time back, and we collect all the information in that time window. So for example, let's have a time. So this is time, right? So we have an error here. So E10, E1 occurred, right? And the fact is that we don't know when they occur. Like for example, here E8 occurs, and it could shortly after, it could be that E1 occurs again, right? So I don't know actually, right? We don't know this. So they are not equidistant, right? So, but what I can do is I can say, okay, for each of these events, I note E1, right? So I put E1 in here. And then I go back a time window, right? I go back a time window of, let's say, 5 minutes. And then I collect all the sensor readings of the last 5 minutes. So this is my window of X1, X2, and X3 at these points in time. And the same I do here. I go back 5 minutes. And the same I go to here. I go back 5 minutes. And of course, this overlaps here, but this doesn't matter. But this is the only way I can do it. And let's have a look. So what I do here is I define a time window, right? I define a time window. So this is the first thing I do. This is a summary, right? So I define a time window from 10:15 to 10:20, and then I use the average of the temperature, the median of S2, and the count of E1, right? And then I have like all my target variables. And now it's important that I have like all of these arrows separately. Like this is a class variable, right? I have all of these arrows separately. So I count them and I say, okay, how many arrows are here? 0, 1, 1, and so on. So this helps me to get a descriptive view, right? This first helps me to get a descriptive view that I can, we are not here yet. We are not there yet, right? But what I can actually do, we can use the descriptive view for data understanding, but we cannot use that for modeling, right? Because still look at this table, right? We have a time window, okay. We have an average, median, a count, right? We have a count of an arrow, but we don't really have the arrow itself. So we have no arrow, which is okay because we also need data with no arrow. So we will use this later on. But what a better way is to transform. We need to transform these times now into actual columns. We need the average at a certain point in time. So this is C. This will actually give us my Y to X ideal. So we have a classification where Y can take on these values, right? So, and then we have some pointers for data engineering here, how we can do it. So what we have here is now we have this exact view. We have the arrow, right? We have an arrow E1, E1, E3, E1. So this is exactly that. We have Y, right? And now we have the features. And what we do is now we have the features of the last, and we take maybe the last 5 minutes, right? So, and what we do is we have when we use time, we can lag them. So we have here, T is the time, this is the arrow. This is basically the arrow at time T, right? This is an arrow at a time T. We're not interested in, we have the time here in addition. We can see this right here, right? We're not interested in the time. The time here acts as an ID for a training example, right? This acts just as an ID for the training example. We're not really interested in the time. This is not a variable we will ever use. I just added it for you because this is the time maybe when the error occurred. And sometimes, of course, it can be that the error occurred at the same time. So just to give you every possible way of doing this. Okay, so we have here S1. And so remember, this is the temperature 15 seconds before the error, right? Then we have the temperature 30 seconds before the error. So we actually don't go into an average view. What we do is we actually use this, right? We have these time windows. We use these original 15 seconds time window. Now I can also use a combination. I can say, okay, I don't want to do it every 15 seconds for 5 minutes. I want to do it every minute. So I could here have the average of T minus 1 minute, and here the average of T minus 2 minutes. I could combine them, right? I don't necessarily have to do it this way, right? So TS of T 30 seconds and so on. But sorry, parenthesis here. And S1, and then I have the same thing, K seconds. The K depends on K is the thing I define the window size, right? So window size. So how long do I want to go back? This is exactly that. How long do I want to go back? Do I want to go back? Then K is large. Do I want to go back short? Then K is pretty small. Okay. So the more values I look at before, right? The larger is, I mean, K is just a multiplication. It's not really, doesn't really matter. Just the way, how long do I look back? So how long is the window, right? That I take. How long do I look back? This is the thing you have to remember. Don't have to remember the K or anything here. Just remember how long do I look back? Okay, this is the idea here. And then for S2 it's the same thing, 15 seconds, 30 seconds, and so on. Okay, so now This is what I have, okay? So, and using this, now I can build a prediction model. I have a training example right here. I have a training example. Now, what we can also use summarizing facts. So summarizing facts, summarizing like this, time distances, be creative and think about what you can get from the data you have and what kind of data you can add. So this is the data we have, right? So this is the data we have. And now I want you to think about, and this shows you that data engineering, and this is what we're doing right here, data engineering, which is part of data preparation. But of course, this is part of this feedback right here from data understanding to data preparation, the ideal bridge for us. And this is now what can you think of? Now you have read this example, right? Now you can do both. You can have summarizing facts, so you can actually use the data you have and add some cool ideas here. Or you can add some new data. This is where the question mark comes in. And now you can be creative. Now you have the scenario and you can either, so I want you to put in the chat, what kind of ideas do you have here to add that could help the prediction? This is where the question marks come in, right? So what kind of assumption do you have? So it could either be, again, you use a summarizing fact based on temperature or vibration, right? Could be a summarizing fact, but it has to fit the line, right? So, or something else. It could be something else where I say, hey, this could, but it has to fit here, right? It has to fit. Now, it has to fit either the window, right? It has to fit either the window. So formulate a variable like, for example, number of people working in the last 5 minutes before the error. This is how you need to formulate it, right? Because it is this window we look for. Or does it have to be? Maybe not. Maybe you have a better idea. Okay, go. There basically are no incorrect answers here. Just might be that they are not as important, but we don't know. We don't have the data. So anything you say, be creative. It doesn't have to be formulated the way I just said. You can also think of another way, right? So let's go. What are your ideas? How can we make this data better? Be creative. Do data engineering. It could be from the data that you have. It could be new data that potentially could be in this manufacturing plant, right? So this is where you come in, where you show me that you can actually analyze a domain and can say, okay, how about we add this, right? How about we add this? There are no wrong answers here, basically, right? Also remember the manufacturing process, right? Maybe use median as 2 levels in the past 2 minutes of the error. Perfect. Yes, absolutely, of course. So what we could do is we could say, okay, in addition of having like these exact readings, what we do is we add a median 2 minutes. Like we want to have like a more urgent window, and we have like as one column the 2 minute median of a 2 minute window, the 2 minute median of S2 of the vibration. Yeah, absolutely. This is absolutely what I'm looking for. Yeah, we could do that, right? So here we would put in here S2, 2 minutes, T minus 2 minutes, and this would be the median. Now, the only thing is like, this is the median over the 2 minute period, right? So we have the error again. What this means is we have the error here. So it's E1. We look at the first line, it's E1. And then we have 2 minutes, right? 2 minutes. And we look at the vibration. We look at S2. We look at S2 here. S2 and calculate the median of S2, right? We calculate the median and put it into a column, right? And this is one number. This is one number, right? So the median of S2 and this is one number. Perfect. Yeah, absolutely. Great idea. More. Be creative. More. I want you to be creative. There are no wrong answers here. Like everything. You could even say the name of my mother at the birth of this. We could put it in. It may not help, but we could put it in. This is not necessarily wrong because we don't know. This is This data set is fiction, right? But you need to be creative. You need to work here, get an idea. As I said, no wrong answers here. What could we do, right? You can think in the same way as Umar did. You can say, hey, we can put in some other things. Now, what are some, if you want to go into the summarizing this, what are some other things that we learned about? Like we just did data understanding. And of course, this is kind of an exercise. Now we did learn centrals of central tendency, right? We also learned about centrals of measures of variation. So this could also be an idea, right? So, and then I showed you other measures that I particularly like that we briefly talked about, but you all know them, right? So go on, come on. Need to be creative here. What are some other measures we can calculate here, right? Or what are some other creative ways of adding? It doesn't have to do with the data at all. It could be like new data, right? Like to help you out a little bit, what you always have to do is you have to come from business understanding. Why we do this is it's a very complex exercise. We come from business understanding, right? What's in business understanding, what you would get is it's not a prediction, sorry, a description of the manufacturing process. So we have this conveyor belt, and then we have like these stations, right? And so we have only like S1 and S2 here. So this is pretty easy, and we only have one manufacturing machine. And there's a product. P1 is being produced on machine 1. So this is pretty easy. We're just looking at machine 1. We know there are other machines, but they are not of interest for us at the moment. So the process could help you understand what there is, like what other things are there. Like there's a product being produced, like and stuff like this. The process of the particular machine that was being used at that time. Yeah. So we could add like data of the machine, right? So we could do this, right? So like some configurations of the machine, for example, for this product. So this product 1 interfaces with the machine. So what's the machine configuration? Yes, this would lead us to having constantly the same value as long as there's one manufacturing process, right? So again, what I have here is, for example, we could have here the manufacturing process ID, like to which process does this belong? So this is the first process, the first process, the first process, first process. And then some point it's the second. So for as long as this is the first process, all the data for the machine would be the same because it has the same configuration for the same product. Now, what if the product changes? Instead of a BMW normal car, we suddenly produce an SUV, right? So it's product 2. And this means that the machine now has different parameters. And then here, if this is the machine parameters, right? Machine parameters, machine parameter 1, it's maybe 0.5, 0.5, 0. Whatever it is, right? It's just, and then here suddenly it's 0.1, right? For this. So we changed it because this, but here it's always the same. But still, it helps the model to say, hey, when we have product 2, something changes, right? And this is very important. We can add some form of machine number for this. Yeah, exactly. So you can add this. So any other ideas? Come on, guys and girls. Come on, you're good. You can do this, right? Go into this direction. Go into this direction or go into this direction. I don't care. This is important. This helps you think about the complex problem. What could we add here, right? So we know we have these two sensor readings and we assume, okay, high temperature is maybe bad, high vibration is maybe bad. So if high vibration and high temperature is bad, what else could be of interest? Like Umar suggested the 2-minute median, right? What could another statistic be, right? If high is bad, like what do we want to know probably? Like what do you, yeah, Marlon, perfect. The maximum value, exactly. It's that easy. As I said, there are no wrong answers. Maximum value, perfect. The maximum value, so we could have the maximum either in a time interval before, right? T minus whatever, right? So the maximum value of this, absolutely true. The maximum value. So we could say before this error, the maximum value was this and that, right? So this is perfect. Yeah, exactly. Totally correct. And this is actually what I thought of when I just told you this. So I'm glad you picked up on this. Yeah. So this could be also 2 minutes beforehand. So I have to, or it could also be the maximum if we have like a 5 minute window. Um, as I said, for these variables, we are not bound to the 5 minute window. We can say, hey, I want to do the 2 minute window and I want to have like the median in a 2 minute window. I could have the maximum in a 2 minute window. I could even have the maximum in a 5 minute window. I could even have the maximum in a 10 minute window. For each of these variables, I don't care what the time window is. Like I just have to know the window to calculate the maximum or to calculate the median. So come on, two more things, and we will wrap up. This is very important. This is not theory. This is practice. You need to do this. This will help you gain analytical thinking. Think about this. It's not hard. Like what else? Like let's say we produce solar panels. We have, look at the process. We have product data, we have machine data. What are examples of this? Like we generally had this, like Umar said it in a general way, but what are specific examples of a product value, of a machine value? Let's say we produce cars, right? If we produce cars, right? What are examples of product value, of product attributes or machine attributes, right? So they belong kind of together. Like if we produce cars, can also say we produce solar panels, right? Did I say what we produce? No. Cool. So it could produce anything, right? Let's say we produce cars, right? So I mean, this is what you have to think about. What can influence? What can lead to the error? What can influence the machines? Their configuration, and what influences their configuration is what I produce. This is why you always have to visualize the process. And with that, I want to make kind of a closing statement for today's lecture, which is a nice bridge to data preparation, but which is true for everything. So this is maybe not so optional, right? So this, of course, is again an optional example that teaches you. So I will not ask you about this example, and you will not have to like do this in the exam. So don't worry about this. However, it helps you to understand how we can build a data table for prediction. And this is because this is the thing you spend most days working on, right? So you've heard a word from me today that was kind of important. I'm going to try to write it. I know my handwriting is really bad, but I'm going to write it. Data generating process. Data generating process. You always have to at least think of what lies behind a data table like this. What lies behind a data table like this? What lies behind a data table like this? Like this is the raw data we get. What lies behind it? What is the data generating process? And the data generating process is this, the manufacturing process. Like what leads to the temperature? What leads that the temperature is there? At least we turn on the machine, and then we manufacture a car, and out comes a car. So look at how cool I can draw cars, right? Oh my God, I drew a Cybertruck, didn't I? Oh my God. This was purely by accident. So I have a car, right? So maybe I do a cool thing here. So it's not oh, it looks even more like a Cybertruck now. Okay, so I produce a car, and this is a manufacturing. This is the data generating process. So where does the data come from? You need from the business understanding. This is why we teach the business understanding. It's not like, oh, I built a model, I know how to do machine learning model. You will not be able to build that unless you know what actually generates the data. And this will help you, like visualize the process that generates the data. What else is there? What are stakeholders at the process? Like what is involved in the process? We have a machine. There is a product. We have the sensors, right? So for example, even something as absurd as like how old is the sensor, right? It could like if the sensor is really old, it could be that the sensor is broken and stuff like this. Like everything would be correct answer here. We then have to filter out a little bit. However, there are a lot of things that we can talk about, like the machine. How long has the machine been running? Like how long, right? Running time. Running time M1, right? Running time M1 until the at the time of the error, right? At time of error. At error. Like how long has the machine been running, right? Um, Running time, and then we can even split this productive, like when it was really productive or when it was idle. Like what was the idle time before the error? Like was the time idle? Was it not idle? So we can even split this up into 4 variables. Like was it idle before that in the last 5 minutes? Idle in the last 5 minutes? Yes or no? And then we can have another variable like idle time. Idle time. So, and if the idle time is, this will of course connect. If it wasn't idle before, then if it was not idle, then the idle time would be 0, of course. But if it was yes, then we would like to know what's the idle time. And these are all variables we can use, right? So, okay. So we're done for today. So this was a practical example. You find the clean version of this. You find the clean version of this that you can yourself annotate as a download in the e-learning, as always, right? So you can check it out. You can make your own ideas about, and I really encourage you to do this. Also, check out RapidMiner if you like. Important message. Next week, there will be no lecture. So you have a break from me. This is why I put all of this today. So you need a break from me after this, obviously. So I will of course put it in the e-learning that there's no lecture in the schedule, so don't worry about it. Just a little heads up, there will be no lecture next week because I'm at the conference. So sometimes they are in semester, which I don't like, but I kind of need to attend this, so there's no way around it. But after that, we will again have a lecture, so you can have a break from me next week. With that, I want to thank you so much for attending today. And we will talk about the week after next week. We will talk about data preparation and some cool problems that we can face and how we can tackle them. And then we will go into modeling, which will be the main part of the lecture. Thank you so much. And as always, you can start asking your questions right now. Thank you.